Hello friends, thanks for watching another video. On the screen, I have the 6 equations that we developed in the previous 2 videos. Some of you may still have questions as to how these equations can be visualized. Here are 2 common questions. Question 1. How do I visualize Ampere's law inside of a wire conductor? Question 2. How do I visualize Faraday's law inside of a wire conductor? To answer these questions, I have created a diorama of the electromagnetic fields inside of a wire conductor, and I will show you this diorama now. This model shows the electromagnetic fields inside of a wire conductor. This model assumes that the electric current in the wire has a frequency of 0 Hz. An electric current with a frequency of 0 Hz is also called a direct current, or DC. This red line is located at the center line of our wire conductor. It represents a differential element of electric current. In other words, it is a small bit of the electric current that is flowing down the wire. As shown by this green arrow here, the electric current comes out of the screen towards you, the viewer. These 3 blue lines here represent magnetic field lines. As shown by these 3 green arrows here, the magnetic field lines are all moving in a counterclockwise direction. This model demonstrates Ampere's law, which is shown here. This law states that current density J will create a curling magnetic field H. So the electric current in this conductor, including this differential element in red here, creates these curling magnetic field lines here. And this magnetic field is curling because it is traveling in a closed loop, in this case, in the form of a circle. Faraday's law of induction does not apply to this model, and I will explain to you why. This law states that a changing magnetic field creates a curling electric field E. However, the phasor form of this equation shows that the magnitude of the electric field depends on the angular frequency of the electric current, as represented by this lowercase omega. So, if the frequency is 0 Hz, then no electric field will be created. So, this model only shows magnetic field lines. There are no electric field lines shown. Here, I have 2 red lines. Each of these lines represents some differential element of electric current. Let's say that each red line represents 10 amperes. When these red lines pass through the magnetic field, their value does not change. So you start with 10 amperes going into the magnetic field, and you end up with 10 amperes coming out of the magnetic field. This model also shows the electromagnetic fields inside of a wire conductor. This model assumes that the electric current in the wire has a frequency greater than 0 Hz. An electric current with a frequency greater than 0 Hz is also called an alternating current, or AC. Like with the previous model, this model also demonstrates Ampere's law because the electric current creates a curling magnetic field. However, this model also demonstrates Faraday's law. Faraday's law of induction does apply to this model, and I will explain to you why. Because the angular frequency is greater than 0, this law shows that the magnetic field will create a curling electric field. Here, you see that for each of the three magnetic field lines, I have drawn a yellow ring. These yellow rings represent electric fields. So, this model demonstrates that a changing magnetic field creates a curling electric field. And you see that the electric field is indeed curling because I have shown it moving in a circle. And these three green arrows shows the direction that the electric field is moving. This model shows that these three magnetic fields have created three electric fields. However, these three electric fields will merge into one, as I will demonstrate in the next model. Here, you see that I have combined the three electric fields into one large electric field. This green arrow shows the direction that the electric field is moving. Now, Ohm's law teaches us that any time you have an electric field inside of a conductor, an electric current will flow in the same direction as the electric field. That means that this yellow circle can also represent a circulating flow of current. This is known as an eddy current. This eddy current has a significant effect on the operation of our wire conductor, which I will now demonstrate. Let's pretend that the magnitude of this eddy current is 1 ampere. Now, I have the same two red lines that I showed previously. Each of these red lines represents 10 amperes. What happens to the value of these two red lines when they pass through the magnetic field? When this outer red line passes through the magnetic field, you see that the eddy current of 1 ampere is flowing in the same direction. So, you have 10 amperes going into the magnetic field, and you will have 11 amperes coming out of the magnetic field. Now, when this inner red line passes through the magnetic field, you see that the eddy current flows in the opposite direction. So, you have 10 amperes going into the magnetic field and 9 amperes coming out of the magnetic field. Let's look again at Faraday's law. You notice that the magnitude of the curling electric field is directly proportional to the angular frequency of the electric current. This means that if we increase the frequency of the current, then the electric field will be stronger. We will demonstrate what happens when you make the electric field stronger. Because you have made the electric field stronger, you have made the magnitude of the eddy current bigger as well. So, let's say that the magnitude of the eddy current is now 2 amperes. What happens to the value of these two red lines when they pass through the magnetic field? When this outer red line passes the magnetic field, you see that the eddy current of 2 amperes is flowing in the same direction. So you have 10 amperes going into the magnetic field, and you will have 12 amperes coming out of the magnetic field. Now, when this inner red line passes through the magnetic field, you see that the eddy current of 2 amperes flows in the opposite direction. So, you have 10 amperes going into the magnetic field, and you will have 8 amperes coming out of the magnetic field. In the demonstration, we saw that as the frequency of the electric current increased, the magnitude of the eddy current also increased. As a result, the current distribution became altered so that the current became increasingly pushed toward the outer edges or skin of the conductor. This is known as the skin effect. When the frequency was 0 Hz, we saw that the differential elements of current was 10 amperes here and 10 amperes here. But when we increased the frequency above 0 Hz, we saw that the differential elements of current became 11 amperes and 9 amperes, meaning that the current became pushed towards the outer edge of the conductor. When we increased the frequency even more, the elements of current became 12 amperes and 8 amperes. So this demonstrates that as the frequency increases, so does the skin effect. To further demonstrate the skin effect, here is the cross-section of a copper conductor with a diameter of 0.2043 inches and carrying a current of 1 ampere at 0 Hz. We see that at 0 Hz, there is no skin effect because the current density distribution throughout the cross-section is constant. Now let's see what happens when we increase the frequency. Here's the cross-section at 60 Hz, 600 Hz, 6,000, 10,000, 20,000, 30,000, 40,000, 50,000, and 60,000. Based on the way the current density distribution changes, we see that the skin effect increases with frequency. Okay everyone, that's it for this video. If this video is of value to you, then please like, comment, and subscribe, and I'll see you at the next video. Thank you.